Welcome to Unit 3, Lesson 8. As usual, you're looking for the tasks to complete for U3L8, so tasks for U3L8. So you can find it under assignments or on the weekly calendar on today's date. This is Friday, December 4th. We'll start off in breakout rooms chatting about a question again. I'm going to put it in the chat right now. Question is, what's your favorite place you've ever visited? What's your favorite place you've ever visited? Think about that for 20 seconds, and then we'll come back together to share. Welcome, Sloan. We're about to go into breakout rooms to answer what's your favorite place you've ever visited. And remember to check in and say hi with the person you're with too. All right, we'll come back together in 2 minutes. Rooms are open. All right, everybody. Next on the docket is just quick homework review. All you had to do was the Edpuzzle and make sure that you completed the classwork on the heating curve of water. Edpuzzle's looking good. Seeing probably about 10 or 11 responses here. Remember, there is an alternative Google form if you weren't able to complete it. But pretty cool that I was able to get the water to actually boil. So did everyone see that the beaker did start to boil, even though it was only 80 degrees Celsius? I didn't heat it up or anything like that. That machine is sucking air out of the container. That seemed to be a question that was hard for a few people, that the machine I switched on was a vacuum. And what it's doing is decreasing the air pressure. So again, you've got to get it in your minds that boiling point is this relationship between vapor pressure in the liquid and atmospheric pressure pressing down on it. And when they're equal, that's when you'll get boiling occurring. So that's how I got that water to boil. I didn't heat the water up. It was still at 80 degrees Celsius. What I did was I lowered the air pressure to the point where vapor pressure and air pressure equaled, and then it started to boil. And then the minute I switched it off, it stopped boiling again because the air pressure increased. Because at Stevenson, we're at sea level. It would have to be 100 in order to boil. So anyway, I hope that was informative. We're gonna continue, we're gonna wrap up our states of matter today and move into gas laws and a little bit of math. But before we do that, I wanna show you one last cool thing with transitions, which is the atmospheric pressure can crush. So this is our first of 2 classworks we're going to do today. We're on tasks to complete step number 3. There's an assignment there, atmospheric pressure can crush classwork. I'd like you to click on, and it should look like this. There's a little intro video, which I'll play for us all right now, and then I'll let you go to work on the Edpuzzles and some of the questions. So let's check this out real quick.
Hi, Sci2C kiddos. Going to use this video as a demonstration of what's called the atmospheric pressure can crush. Now, you can either just watch this video, or an optional alternative is you can try this at home. However, you do not have to. This is a little bit dangerous, but I'll walk you through what you need. Safety is going to be the most important thing, so you need some kind of eye protection, glasses or sunglasses. I've got my lab coat on, and something to protect your hands. You're working with boiling water. That's the main thing that's dangerous, as well as a hot surface. So oven mitts or something are good too. Let's do some science. Now, what you're going to need if you do try this at home is an empty aluminum can, as I mentioned with the homework. You'll need a bowl with some water in it, just regular sink water, and it doesn't have to be glass. Glass just makes things more visible. And so you're going to fill the glass bowl with water from the sink. You need to fill the can about 1/4 full of water. You really don't need that much. I mean, I would use about this much or so and just pour it on in there, like so. And you're going to need tongs to grab this can, because what you're going to be doing, as you can see over here, is heating the water in the can on a stovetop. And you'll want to keep it going until you hear that. I'm not sure if it's coming through in the video, but you can kind of hear it bubbling in there. And there's a, you can see the water vapor coming out of the opening on the top here. So then what you're going to want to do is use tongs, again, because you're going to grab the edge of the can here, like so. And what you're going to do is you're going to invert it upside down into the water. So you want the opening on the top to go into the water. Okay, so that's what I'm going to do. Again, be very careful if you're trying this at home. You don't have to do this at home. You can just watch this video to answer the questions. But if you want to give it a try, have some adult supervision, someone to help you, and just make sure you're being safe. Keep your distance. So watch what happens when I now take this can that has boiling water in it and place it in the water. Here we go. Now, you'll notice the can imploded. And that wasn't me squishing it with the tongs. That was something else going on there. And so the question you'll need to answer as part of the Canvas quiz you're working on is why that happens. So again, please answer the questions in the quiz. If you're going to try this at home, please be safe.
All right, quick show of hands. How many of you have seen something like that before? A can being imploded by just being dipped in water. Some of you a little bit. It's pretty cool. So again, that wasn't me. The can just went right in on itself. That was not the tongs or anything that I was doing with squeezing. And what's happening is something to do with phase changes. So on the quiz below, again, it's optional. If you want to do a flip grid and try this at home, you can, but it's not graded. It's not something we're going to require. Please be safe if you do try to do that. But otherwise, there is a little prediction question, right? I'm going to ask you, like, why do you think? There's no right or wrong answer. Just what are your thoughts on that? There's an ed puzzle you'll watch, which will explain it, another question, and one more ed puzzle for you to work through. And then you can type complete on the quiz. You'll notice for the ed puzzle questions, I've embedded the ed puzzles, but you can also click on a link. But there is a prompt. There's a question box on the bottom. All you need to do is type done in there once you've watched the videos. There's no question associated with that. The questions are in the ed puzzles. But there are two other separate questions in the quiz itself. I'm going to time for 20 minutes to let you work through this classwork Canvas quiz. Hopefully it won't take that long to get through. I'll watch your progress on ed puzzle and on Canvas. I'll be here listening if you have questions or need help. Go for it. 20 minutes to complete the classwork quiz. If you want to try the flip grid, you can try that and then come back to the quiz later. Which should look like this, where you've got a couple blanks to fill in, some more math to do with just blanks. And again, I'll instruct you on when to tackle these, and I'll provide you with the information you need as we go through. So open up that quiz. I'm going to set up my iPad here on the screen. And just bear with me
I
as
have
we...
a question.
Yes.
So I have to go early, so I did the quiz with the slides.
Okay, that's all right.
Is that okay?
Yeah, that's fine. Yeah,
Okay,
all the answers are there. So
yeah, I just turned them all in. But the problem is I got the last question wrong, and I did the math right. I just included the with the zero at the end. Like I put another digit accidentally, so sorry.
Yeah, I'll probably notice, or you're welcome to. You can do a second submission. I know it's a lot of work to fix one thing, but yeah, I'll probably notice and can make a manual correction. So, thanks.
Thank you. Have a nice day.
You too. Enjoy the weekend.
Thanks.
All right, everybody, give me a verbal confirmation. We see nature of gases on the screen.
Yep.
Yes.
All right, here we go. Friday evening. Bear with me. So we are going to assume a model of gases. What this means is there are three assumptions that we are going to make about gases, right? The air around you and everything else. One, that it is composed of small, tiny particles. So think of those little dots there as O2 molecules, or N2 molecules, or helium, He, which is essentially what air is composed of. We can assume that these particles are constantly moving. You saw this in the PhET simulation. I have the link for it right here again. Where, remember, the gases, you could watch those particles literally just bounce around everywhere inside the container they were in. We're going to assume that that bouncing is elastic, which what that means is there's no energy gained or lost. So if you have two gas molecules that bang into each other, they are going to repel off with just as much energy and just as much motion as they started. So there's no stopping or merging together or anything like that. So that's the assumption. Now, in reality, that is not what gases are like, but we need to kind of get an ideal picture of them so that we can then explain these gas laws. So just imagine, like the PhET simulation, there are particles bouncing around. And it's that bouncing, every time a particle hits the edge of something, that's what creates pressure. So we've been talking about air pressure and atmospheric pressure. That's just all the air molecules around you bashing into you. You can feel this by waving your hand around in the air, right? You can feel the air. And those are just the particles that you're colliding with. And so trapping these in a container, all those collisions can create pressure inside, and you can then change volume to increase it or decrease it. Those are the relationships that we're kind of building up to here. So in terms of how do we actually measure gas pressure, like how do we measure atmospheric pressure, you use what's called a barometer. Some of you might have one of these outside your house if you've seen these before. And it's just measuring the force exerted by a gas on the surface of an object, which is usually you walking around, right? And so barometers usually are going to show, like, you can kind of predict the weather a little bit. It's not entirely accurate, but as you can see, higher pressures tend to yield nicer weather. Lower pressure means you've got storms coming or something like that. You can talk about high pressure systems and low pressure systems. Okay, so if we're measuring pressure, what are the units? We're usually pretty familiar with units of distance and units of weight, right? Meters and grams. Pressure, I think, isn't something that immediately comes to people's minds. So the standard unit for pressure in science is called a kilopascal, or kPa. But there are ones that are more commonly used, right? Hopefully most of you are familiar with what's called PSI, pounds per square inch. That's how we tend to measure things in the United States. If you remember the whole Deflategate thing with the Patriots, they kept talking about the pressure of the football and PSIs. We also use what's called millimeters of mercury, which I'll explain in a second, and atmospheres, which I like because it's just a nice round number. At sea level, it's 1. But here are the relationships between those different units. So it's kind of annoying, but you have to know how they equal each other. So 1 atmosphere is the same as 760 millimeters of mercury, 101.3 kilopascals, or 14.7 degrees or PSI. So on your quiz, that's your first question. Please enter those numbers into those 4 blanks on that very first classwork quiz question, just to show me you're following along. The reason I'd like you to note this down is we're going to talk about how to convert from one unit to another, which is going to be an important thing you're going to need to know how to do. All right, again, if you're still entering numbers, you can open up the slides themselves and see the same information. So what's going on with that millimeters of mercury measurement? That seems a little weird, right? Millimeters is a measure of distance, not pressure. And it's based on the original barometers. This is what they look like. It was liquid mercury, which is a liquid metal, very toxic, not something you want to expose yourself to. And they would insert a glass tube. You can't see it, but on the inside here, it would be open like that. And what's happening is then atmospheric pressure is pressing down on the surface of that liquid, and it's forcing some of it up this tube. And so you just grab a ruler and you can measure along the edge here in millimeters. And that's what millimeters of mercury is based on. And there's a vacuum at the top, meaning there's no significant amount of gases in there to create pressure or anything like that. So it's just the liquid mercury moving up and down. That's just the origin of that, something we'll come back to in a little bit. Okay, the gas laws, which we're going to spend the next few classes on, are describing the relationship between 4 variables, 4 things about gases. First is pressure, which I just mentioned is measured in all these different units. There's also temperature, typically measured in Celsius, degrees Celsius, but you can also have K. Anyone know what K stands for?
Kelvin.
Very good, right? Scientific unit for temperature. You can convert between Kelvin and degrees Celsius just by adding or subtracting 273. So there's a good conversion to know. If you've got Celsius and you need Kelvin, you just take your Celsius and add 273. If you've got Kelvin, you need Celsius to subtract. Volume is measured in either milliliters or liters. And then we also have moles, which is the amount of gas present. We're not going to spend much time on moles in particular because that's a whole other thing we could do. Plus, I think PSI touched on this a little bit last year. So we're going to focus on these 3: pressure, volume, and temperature. Specifically, what the gas laws are describing is what happens when one increases. Like if you were to increase the pressure of the gas, what happens to the volume? What happens to the temperature, right? What are the relationships there? Are they direct or inverse? Before we get into that though, let's talk about unit conversions, because this is just a good little mathematical trick. You have to use ratios of equivalent measurements, right? Equivalencies. So bear with me here. I'm going to hopefully assume that you all recognize that 1 meter is the same as 100 centimeters. So you can see these are 2 rulers. They're the exact same length, but they're measured in 2 different units. You can create a fraction or a ratio based on that. This would be a ratio of 1, right? 1 meter is the same as 100 centimeters. Or I could flip that on its head and say 100 centimeters is equal to 1 meter. The reason these fractions are helpful is because we can then use them mathematically to convert from one thing to another in more complicated examples. But I'll start off with a simple example. Everyone knows that $1 is equal to 4 quarters. This is a currency in the United States, right? And so with that relationship in mind, let me pick an arbitrary number. Let's say, what if I had 12 quarters? Can anyone tell me right now how many dollars would I have if I had 12 quarters?
$3.
Yeah, and most of you can do that in your mind, right? No problem. But I want to show you how to do that mathematically using these fractions. So what's going to happen is, and this is just a habit I want you to get into because I think it's really helpful, is if I wanted to convert this into dollars, so I want blank dollars, that's where I'm headed, then let's use this ratio. I need to put quarters on the bottom and dollars on top. Here's why. Does everyone know if I've got quarters on top here and quarters on the bottom here, what are those two units going to do to each other?
They're going to cancel out.
They cancel out. Very good. So all I'm left with is dollars, which is what I wanted. I need to find this relationship. What's the relationship between dollars and quarters? There it is right there. So I know that 4 quarters is equal to $1. And so you're going to do 12 times 1, which is 12, divided by 4, which someone pointed out is 3. And so we have $3. I know it's a little confusing because it looks like a fraction. So let me delete all that. It's just $3. We'll just use the dollar sign for that. Okay. Now again, that seems like a whole lot of work and math to solve a pretty simple thing, right? You could just do that in your head. You're not going to be able to do things like this in your head, where you've got these really goofy numbers to convert between different measurements. And let me provide the, remember again, if you need Kelvin, you know your degrees Celsius, then you just need to add 273 to your degrees Celsius. So I'm going to walk through this example here for you. You have these same problems on your Canvas quiz, so I'd like you to give them a try. But I'll do the top 2s as an example and then let you go to do the bottom 2. So first one, 2.5 atmospheres, and I want to know what's the equivalent in kilopascals. So once again, set up 2.5 atmospheres, multiply by a fraction, and I know I want to end up with just kilopascals at the end there. So I'm going to put atmospheres on the bottom so that they cancel out. I'm going to put kilopascals on top because that's what I want to be left with. I need to find that relationship. If you look up here in the conversion box, 1 atmosphere is the same as 101.3 kilopascals. So 1 atmosphere on the bottom, 101.3 kPa on top. Do the math and you get a big number, 253.3. 253.3. So put that in there. Okay, temperature is super straightforward. If I need to know the kelvins, then I know that it's going to be 73 degrees Celsius plus 273, which comes out to be 346. There you have it. So go ahead and use those same models. Try those last 2. Convert 511 millimeters of mercury into atmospheres, 500 degrees Celsius into Kelvin. You have not done so already. All right. Can you tell me what they got for B? What is 511 millimeters of mercury equal to? Anybody do it?
0.672 atmospheres.
Very good. Sounds right. And not surprising that we got a small number, right? Because notice the relationship, right? We know that millimeters of mercury, it's 760 to 1 atmosphere. That is less than 760. So you know you're going to get less than 1 in terms of atmospheres. Good way to check yourself. For this one, hopefully it was pretty easy. If you're just adding 273, you're going to end up with 773, right? Did I do the math right on that? Yep. All right, you can see the same solutions on the slides themselves. Okay, any questions or comments on that? All right, we got one last thing to try here. Let me introduce your first gas law, Boyle's law. Boyle's law states the following: pressure is inversely proportional to volume. So in other words, if the pressure of a gas goes up, the volume is going to go down. They will do the opposite. Vice versa, if the pressure goes down, then the volume will go up. And you can say that the other way around too. Notice we're ignoring two variables here. We're going to assume that temperature and the amount of gas, the moles, those are staying the same. We're not going to include those in our mathematical equation. So don't worry about temperature or anything like that. The equation is written like this: P1 V1 equals P2 V2. Again, just mathematically speaking, that works out that since they contradict each other, they're inverse. That's how you set it up. They're multiplied by each other. Pressure is measured in any of these units as long as they're the same. As long as P1 has the same unit as P2, you're good. Same thing with volume. Volume could be milliliters or liters. They just have to match each other, and you're all set. So this is kind of just plug and chug math at this point. Let's take a look at an example problem. Half the challenge of these is just identifying the variables. You have this same practice problem in your Google Canvas quiz. So if a balloon is filled with 425 liters of helium gas, I'm going to call that V1. Everyone see that's our first volume. It's kept at a pressure of 101.3 kilopascals. I'm going to call that P1. That's the first volume and first pressure that we're given. Oops, my bad. What did I mess up here? No, yeah, that's good. If the balloon floats away and reaches a high altitude, changing pressure to 47.2 kilopascals, that's going to be our P2. Then what would the new volume of the balloon be? V2. So we don't know V2, second volume. We know that that's what we're solving for right there. Before we even do some math, I'm hoping that you guys can make a prediction. Can anyone tell me what happened to the pressure? What happened between P1 and P2? Did it go up or go down? Did it increase or decrease?
Decreased.
Decrease.
And so,
Decrease.
if it decreased, then what do we expect the volume to do?
Go up.
Very good. So our volume, V2, should be a higher value. It should be greater than 425 on our final answer. So there's two ways you can approach this. I know some people like to rearrange the equation. So just to show you really simply, like how would we solve for just V2 on its own? All you need to do is divide both sides by pressure. In other words, you're bringing P2 over here as a fraction. So you could rewrite the equation as just P1 V1 over P2 is equal to V2. So we'll see how I just divided both sides by P, just brought the pressure over as a fraction. So that's the equation you would use to solve this. I don't tend to work that way, but I mean, you can do however you want, whatever works for you. I like to kind of plug in the numbers and then go from there. And so for me, that would be like this. Here's the pressure, P1 and V1. We know those multiplied by each other are equal to the second pressure times our unknown volume. And like I showed you there, we're just going to divide both sides by that pressure. So I just brought 47.2 over here as a fraction. And so you just need to solve that. 101.3 times 425 divided by 47.2. Use a calculator. You should get something like 912 liters. Notice kilopascals cancel pressure. That's why we're only left with liters. Anytime you have the same unit on the top and the bottom of a fraction, they'll cancel out. So with that in mind, go ahead and try the second example right here. A diver with a tank of 50 liters and an oxygen gas of 3.20 atmospheres. Pressure, dives for an hour. Afterward, the dive, the pressure of the tank is 203.6 kilopascals. What volume of oxygen was left in the tank? Show your work. Just to give you all a warning about this one, I'm hoping that you all notice something about P1 and P2. What's a sort of an added challenge in this question? Can you tell me?
Different.
Very good, they're different units. Uh-oh. So you just need to choose one and convert it, right? Just like what we were talking about. You need to convert atmospheres into kilopascals, or kilopascals into atmospheres, however you want to do it. All right. Hope that was enough time to at least make some progress on this. If you flip to the next slide, you can see the solution here. So I chose to convert into atmospheres. I just like atmospheres a little better. But the math should work out either way, no matter what you do, whether you convert it to atmospheres or whether you convert it to kilopascals, you should end up with the same answer because things always end up being proportional. But I took 203.6 kilopascals, used the relationship of 1 atmosphere for 101.3 kilopascals. Those cancel out. And I'm left, I know that's the equivalent of 2.01 atmospheres. So in other words, I replaced that number with 2.01 atmospheres. Then you just plug all those numbers in, your V1 and your T1, sorry, P1, your P2, and we're trying to find V2 once again. That's what we don't know. And again, divide both sides by the pressure, get the atmospheres out of the way. You should have ended up with something like 79.6 liters. Again, notice atmospheres cancel each other out. You'll have a homework problem that's related to this. I'm still putting the homework together. Honestly, it'll be sort of an Edpuzzle quiz. But please refer back to these if you're having trouble, and we'll keep practicing this. In the real world, this has applications for scuba diving, or if anyone's ever swum really deep down underwater. This is the relationship, right? Again, we know that as you go deeper and deeper in water, pressure increases. And the reason that you often feel that pain in your ears, if any of you have been scuba diving, or again, if you've dove down to the bottom of a pool, your ears feel really painful. And that's because as the pressure is increasing, there's actually little bubbles of gas inside your ear, your internal structure, and the volume is decreasing. So your inner ear is literally being crushed because the gas is shrinking. And so all of that bone and tissue is also imploding in on itself. Luckily though, and again, I wonder about this from an evolutionary standpoint, I don't know what's going on here, but you actually have a little bit of an air passage connecting to your ears, right? You can apply pressure to your nose, right? Hold your nose closed and really try to blow air out of it. And that air will then escape through your ears, and that's what we call equalizing. So if you've ever been scuba diving or anything like that, they'll often tell you need to equalize, because scuba divers, they go deep, deep, deep down, their ears will really start hurting. And so they do that same motion, much like you would do to an airplane, to relieve the pain by pushing more air into that space. This is also why, again, when they rise back up, their ears will crack a little bit or pop because that gas is then expanding and escapes out of past the eardrum a little bit. So, alrighty. Thanks for bearing with me through that. I know that was a lot of just slides and math, but I hope that classwork was a little helpful. Once again, I'm still trying to put the homework together. I'll get that done as soon as I can, definitely by the end of this evening. It'll be a little Edpuzzle and quiz that you'll complete. Any questions or comments on that? All right, kiddos, that is it for me. Enjoy the weekend. Stay safe out there. Thanks a lot.
Thank you.
Thank you, you too.